All right, so we're going to go over our specification of our model or specification of our regression. So we're looking at price. We're regressing price onto square feet. So price I is equal to some intercept plus some slope multiplied by the square feet, or the square footage of the home, and we have our error term. So in order for a linear regression to be reliable, it has to follow the Gauss-Markov assumptions. So this would be the classical linear assumptions, or this is in chapter 2, chapter 3. It's also something that you would see in an introductory econometrics class. But anyway, so if it violates any of these assumptions, then the model may not be reliable, or it may not be a good model to estimate or to predict. So for these assumptions, the assumptions are one. So for one, it has to be linear. It has to be linear in the parameters. We can see that this, in our specification, it is linear in parameters. We have an intercept and a slope, so it's linear. This is linear, so we're good there. And for two, for the second assumption, the data has to be a reasonable sample of what we're trying to estimate. So it has to be a good sample. So it has to be a good sample. So this means that if we have this population of homes, and we collect a sample, so this is the population, and we pull a sample out of that. If we use the sample to estimate our coefficients, or to estimate the coefficients for our model, and to predict other things in this population, the sample has to be a good representation of the population. So in our sample, we're looking at home sales, or at sold homes from January 2010 to December 2015. And these are specifically in Charleston, South Charleston, and Dunbar. So if we're looking, maybe if we are going to compare or build a model, estimate a model or regression model for home sales in 2016, maybe that's not too different. So maybe we would have a sample okay for that, but maybe this wouldn't be a good sample for trying to estimate home prices in, say, Morgantown, because it's too far, or wouldn't be a good sample to estimate home prices in New York. It's a completely different population. So you'd have to keep that in mind. But if we're just looking at Charleston area in West Virginia in a similar time frame or similar time, then this may be an okay sample. But of course, you couldn't use it to estimate home prices in 2008. You may not be able to use it to estimate home prices in 2020, but you'd be able to estimate home prices around that time. So then for the number 3, so for the third assumption, none of the independent variables are perfectly collinear. So this would mean that, say we included square feet, and say we included number of bedrooms. If these two are correlated, which they are, then that would be a bad model. That would be bad. You shouldn't include them both. So this is talking about collinearity between the different independent variables. So for this, in order to be a good model, the independent variables, the explanatory variables, should not be collinear. For our fourth assumption, the expected value of the error term is 0. So this means that the expected value of our error is 0. So remember the expected value in the moments from the previous module in probability. This would mean that if we took the expected value of price, so if we took the expected value of price, this would be the expected value of a constant, just a constant, so that would be beta 0. Then the expected value of beta 1 times square feet, you can factor out beta 1, which would give you the expected value of square feet, plus the expected value of your error term. The expected value of the error term is 0, so it has to be 0. So the expected value, or the mean of the error term, has to be 0. Then for the fifth assumption, the variance of the error term, the variance of the error term has to be constant. So we're going to say the variance of our error term is equal to some constant variance. So it's not, so it could be any variance. It could be any number as long as it's positive. So it has to be greater than 0. It has to be a positive number, but it can be any number. It could be any number. And then for the final one, the final talks about autocorrelation or serial correlation. So this is 6. The error term is uncorrelated across observations. So this would mean that our correlation between our error terms, let's say in group I, and then since error terms, the correlation between I and J is going to be 0. So this means that they are not correlated, that there is no autocorrelation. So these are the Gauss-Markov assumptions that are important for regression analysis. And then in the next videos, we'll go over each of these, and we'll see whether or not the model that we're estimating, if it violates any of these assumptions. And if it does, then it would not be a good model to predict home prices.